All right, we're gonna figure out how to do trial one of determination of equilibrium constant. There is a calibration curve in your lab manual, and this is the calibration curve that gives you this equation here that it shows right here. So this is the curve that you'll be given. Absorbance on the y-axis, concentration of the complex ions on the x-axis. So you use y as absorbance, x would be your concentration, and 4713.6 is literally just the slope. So that's where this comes into play. If your absorbance is 0.1, you put your 0.1 right here, you can actually get the concentration of, put your 0.1 at y, x will be the concentration of the complex ion that you need at equilibrium here. Okay, so that we'll do in a little bit. But over here, let's take a look at the initial moles calculation. Initial moles depends on how much volume you put in. So you can see I wrote 5 moles here times the molarity of the solution and 1 mole here times the molarity because our table of how much we use is right here. 5 moles for trial 1, 1 mole for trial 1 for KSCN, and this is FeNO3. Okay? So the molarities are given as well. So let's go ahead and convert this. You have to convert it to milliliter, from liters to milliliters first, and then do the molarity. So the molarity is given 10 to the minus 3 moles of SCN negative over 1 liter. Okay, so let's see what we get over here. When you put this into your calculator, you should get 2.00 times 10 to the minus 6 moles of SCN negative. Okay, now equilibrium of FeSCN here, literally all you take is put the absorbance, which is y, 0.10 equals to 4713.6, and then concentration of FeSCN at equilibrium. Okay, which then you solve for the FeSCN by taking 0.1 divided by that number. And you get that value to be 2.12 times 10 to the minus 5 molarity of FeSCN. Okay, so that's the answer for that right here. This was just the work. Now, then they say, what's the equilibrium moles? So if you know your molarity, you need to know your moles because molarity is moles over liter, right? So basically, if you want the moles, you already have the molarity from here. We need to know the liters of the solution, which the liter of the solution, this is going to be the liter of the total overall, which in our case, we use 10 mils total. Now, keep in mind, the formula does say 10 mils here, but if you have an exam, perhaps or a later quiz, it might not be 10 mils in there, and that number will change accordingly, okay? So all I'm going to do is to figure out the moles is put 2.12 times 10 to the minus 5 molarity, okay, equals to whatever the x mole is, right? We don't know what this is, over 10 mils, and divide that by 1,000 to get liters, so 10 divided by 1,000, you get 1.00 times 10 to the minus 2. Okay, now all you do is you solve for the moles here. So that answer would be this times that. So that times 2.12 times 10 to the minus 5. You get 2.12 10 to the minus 7. Okay, so that's how you do it. So that's that answer. Let me box it up. That was the answer here too. And then these two were the answers. Okay, now equilibrium moles of Fe would be basically we have to use something like the table below here on the bottom. So we're speaking moles here. So I wrote a table of moles Fe, moles SEN, moles of product. And you know that the equilibrium constant formula is going to be the products of a reactant. So what I'm going to do is go ahead and fill in the initial moles that I just calculated. So initial moles for Fe goes here. So I'll put this as 1.00 times 10 to the minus 5 here. SEN I found out as 2.00 times 10 to the minus 6. And then moles of FeSEN, we didn't put any at the beginning because these are your two reactants, okay? So initially that one was 0, but at equilibrium we found out that it had a certain number of moles. It was 2.12 times 10 to the minus 7 moles, okay? So this guy went from 0 to that number. That means the change for the product is going up by 2.12 times 10 to the minus 7. So if you wanted to get equilibrium moles, all you do is know that it's 1 to 1 to 1 mole ratio because of our equation, mole ratio is 1 to 1. So if this one, the product goes up by this number, the reactant should go down by the same amount. So it's minus 2.12 times 10 to the minus 7, minus 2.12 times 10 to the minus 7. So you take the initial and then with the change, add the change, which is minus that number, add the change because this is a negative change. 0 plus that gets this. So we'll get answers here. 1.00 times 10 to the minus 5 minus 2.12 times 10 to the minus 7. That should give us a value of basically 9.79 times 10 to the minus 6. And this one should give us 1.79 times 10 to the minus 6. Now, if you have made a mistake by putting in, one very common mistake is students like to put the molarity in here instead of the moles, then everything changes. You end up getting negative values, and that's a really common mistake you want to avoid. You cannot get a negative molarity or negative moles here, okay? So the change here is going to be a tiny change, and it's the same number as a moles of FeSEN. So if you notice the formula on your equation 7, it actually tells you just take initial moles of Fe3 plus minus equilibrium moles of FeSEN, which yes, literally is the same thing, but the reason is because the change is the same amount because it's 1 to 1 to 1. Okay, and remember, when we convert from molarity to moles here, we have to use the total volume in liters. So this total volume here will change according to whatever the experiment setup will be. So you have to pay attention. In our case, this lab is 10, okay? All right, so I have my answer. So let me go ahead and put this up on this table, back up here. 9.79 times 10 to the minus 6 moles of Fe at equilibrium. And then 1.79 times 10 to the minus 6 moles of SEN at equilibrium. Now, my job is now convert them all back to molarity so I can get the K. So I already have the answer for this one from the beginning using the calibration curve, which is this answer right here. So let's go ahead and change this back 2.12 times 10 to the minus 5 right here. Okay, one common mistake is students actually will use the wrong value. Sometimes they use the 10 to the minus 7 and you really get the wrong answer. So just make sure you are putting molarities in here, not moles. You can change it back, okay? So if you wanted to get the equilibrium moles here back to molarity, we use the same formula because our volume is again 10 mils. So we'll take basically the moles here is 9.79 times 10 to the minus 6 moles, right? And then we divide it by the liters, which is 10 divided by 1,000. And then we get 0.0100 liters here. And then we do the same thing for this guy. So let me change this. This one you'll get 9.79 times 10 to the minus 4. This is molarity. And then you do the same thing, 1.79 times 10 to the minus 6 moles over the liter, 10 mils. And then you get 1.79 times 10 to the minus 4 molarity. Okay? Now, this part is going to be important. When you put this in your calculator, you have to put For K, you put 2.12 times 10 to the minus 5. And then on the bottom, you want to have 9.79 times 10 to the minus 4. And then 1.79 times 10 to the minus 4. So these numbers go there. Okay, now put this carefully in the calculator. You should end up getting something like 121, give or take some rounding. Sometimes if you round differently, you get a little bit different answer. That's something you should have, okay? So this is just trial 1. You basically repeat this for 5 trials with all the 5 different absorbances. So I hope this helps. The formula is basically the same as the book, but I just wanted to explain where the numbers came from. So key point is total volume might change. So it's not always going to be 10 on the bottom here. You have to change it to whatever the volume total that you use. And then basically keep in mind molarity is different than moles here. And you can't ever have negative moles or molarity. All right, I hope this helps.